Imagine pointing a camera at the night sky for just 10 hours and walking away with more new asteroid discoveries than most of the world's observatories managed to find in several combined weeks of searching. That is not an exaggeration. 10 hours, thousands of space rocks that no human being had ever recorded before, some of them close enough to Earth, that scientists immediately flagged them for closer tracking. That was only the warm-up act. What this instrument has produced since that first test run is even more astonishing, so if you want to stay updated on every new discovery coming out of this project, now is a great time to hit follow before we dive in. The telescope behind all of this is the Vera Rubin Observatory, and it officially opened its eyes to the public on June 23, 2025. It sits high on a mountain called Cerro Pachon in Chile, tucked into the Atacama region, one of the driest, darkest, and most reliably clear patches of sky found anywhere on the planet. That location was not picked casually. Almost no rainfall, almost no light pollution, and an unusually stable layer of air that does not distort incoming starlight nearly as badly as most other locations on Earth. It is precisely the environment astronomers dream about when trying to extract every last bit of clarity out of a ground-based instrument. For decades, the general assumption in astronomy has been that if you want the sharpest possible view of the universe, you need to leave Earth's atmosphere behind entirely. That is exactly why Hubble and James Webb were launched into orbit and beyond. Ground-based telescopes have always fought atmospheric blur, shifting temperature layers, humidity, and subtle distortions. Invisible to the naked eye, but obvious to a sensitive camera. The Atacama Desert mostly sidesteps this through geography. Extreme altitude, bone-dry air, and distance from city light pollution create one of the most stable, transparent air columns on Earth. Part of why this region hosts several of the world's most important telescopes. Building here let engineers pair an exceptional natural setting with a 3-mirror optical design and automated nightly scanning, minimizing limitations most other ground-based observatories still fight every night. Here's what separates this observatory from almost everything before it. Most telescopes zoom in tightly, picking a single galaxy or star cluster and gathering fine detail from a narrow slice of the universe. The Rubin Observatory does the opposite. Its entire design exists to capture enormous swaths of sky in a single shot, then repeat that process night after night for 10 straight years, building a time-lapse movie of the entire visible sky rather than a photo album of individual objects. At the heart of the system sits the Simony Survey Telescope, built around an 8.4-meter primary mirror using an unusual 3-mirror design. Behind it sits the camera itself, and this is where the numbers start to feel absurd. It is the largest digital camera ever built for astronomy, roughly the size of a small car, weighing close to 3 tons, and capturing images at 3.2 billion pixels per shot. Most phone cameras shoot between 12 and 50 million pixels, so this camera captures more than 60 times that in one exposure. A single picture covers a patch of sky wide enough to fit roughly 40 full moons side by side. To capture the same coverage, Hubble would need thousands of images stitched together piece by piece. The engineering inside that camera deserves its own moment of appreciation, because this is not a large or ordinary sensor. Inside sits an array of nearly 190 individual sensors, each calibrated so the stitched image's seams essentially disappear, producing one seamless picture instead of a visible patchwork. In front sit 3 enormous lenses made of fused silica precision ground glass, one of which is the largest lens ever manufactured for astronomical use. Together, these lenses correct for distortion across the camera's unusually wide field of view. Without that correction, a star near the edge of the frame would appear smeared compared to one at dead center, undermining the precision this survey depends on. The camera can also swap optical filters using a robotic mechanism, capturing ultraviolet, visible, and near-infrared light in quick succession, on each wavelength revealing different physical properties of whatever it observes, from a star's temperature to a gas cloud's chemical composition. This is not a camera in the traditional sense. It behaves more like a multi-layered scientific instrument, where every exposure carries hidden information well beyond a pretty picture. Chemical signatures, thermal patterns, gravitational distortions, even faint trails left by things that move during the exposure. Extracting that hidden structure is the entire point. When the observatory revealed its first test images in June of 2025, the scientific community had been anticipating the moment for years, and what came back exceeded most expectations. Engineers had run just over 10 hours of test observations, a tiny fraction of what the telescope would eventually spend looking at the sky. In that short window, it produced a mosaic nicknamed the Cosmic Treasure Chest, focused on the southern Virgo cluster, the nearest large collection of galaxies to our own Milky Way, built from roughly 1,000 exposures combined into one seamless picture. Inside sat millions of stars and galaxies, spirals with arms stretched across space, pairs caught mid-collision, and faint threads connecting distant clusters like a cosmic spiderweb. Here's the part that puts the scale of this project into perspective. That entire mosaic represented roughly 1/120th of 1% of what the observatory is expected to eventually capture over its full mission. That jaw-dropping first image was closer to a trailer than the actual film. The observatory also released a wide-field mosaic capturing two well-known star-forming regions, the Trifid Nebula and the Lagoon Nebula, both several thousand light-years away, built from more than 600 separate exposures, taken across roughly 7 hours of observing time. Normally, images of these nebulae come from telescopes zoomed tightly into the glowing clouds of gas and dust, filling the entire frame with just that one structure. The Rubin Observatory did something different. Because its field of view is so enormous, the nebula appeared as just one part of a much larger neighborhood, surrounded by open star clusters, dense globular clusters, packed with ancient stars, and countless other points of light that would normally require a separate observation entirely. It was less like peering through a keyhole at one room and more like having an entire house's floor plan revealed at once. Beyond the visuals, the real headline from that first 10-hour test run was what the observatory found moving through our own solar system. In that short window, it identified more than 2,000 new asteroids, several classified as near-Earth objects, meaning their orbits bring them close enough to matter for tracking. To put that in perspective, all the world's combined asteroid tracking observatories working together over an entire year typically identify around 20,000 new asteroids total. This one telescope matched a meaningful fraction of that annual total in less than half a day of test observations before its full survey had even officially begun. The observatory did not stop there. As commissioning continued through the following months, scientists combed through the growing pile of data, and discoveries kept multiplying. Researchers eventually confirmed just over 2,100 new asteroid discoveries from that initial window alone, drawn from roughly 340,000 detections collected across about 9 nights between late April and early May of 2025. Buried inside was something remarkable. An asteroid now cataloged as 2025 MN45, measuring roughly 710 meters across, wider than 7 football fields end to end. What made it stand out was not just its size, but its spin. It completes a full rotation once every 1 minute and 53 seconds, the fastest spinning asteroid of its size ever recorded. Scientists noted that for a solid object that large to spin that fast without flying apart, it would need remarkably strong, cohesive material, holding together against forces that would tear apart a loosely packed pile of rubble. As the observatory moved into full operation, the pace of discovery only accelerated. In a more recent survey period spanning roughly 6 weeks, the telescope logged around 1 million individual observations, resulting in about 11,000 brand new asteroids, alongside repeat observations of roughly 80,000 previously known ones. Some of these newly identified objects pass close enough to Earth's orbit to be worth tracking carefully going forward. Taken together, these results suggest that over its full mission, this single observatory could discover millions of asteroids, comets, and other small solar system bodies, fundamentally reshaping how we understand the population of objects, sharing our corner of the solar system. There is an important practical reason this matters beyond curiosity: planetary defense. Identifying potentially hazardous asteroids long before they could pose a real threat depends entirely on knowing these objects exist. A telescope capable of scanning huge portions of sky repeatedly, catching faint, fast-moving objects earlier surveys would have missed, gives scientists more lead time to study a concerning object's orbit and rule out or confirm future risk. This observatory is quickly becoming one of the most important tools humanity has built for exactly that purpose. Finding thousands of asteroids was just a side effect of testing the equipment. The observatory's actual 10-year mission is built around 4 major scientific goals, and asteroid hunting is only a fraction of one of them. The second goal focuses on something this observatory is uniquely suited for: catching transient events, anything in the sky that changes, flares up, or disappears, on a timescale ranging from minutes to a few days. Because the telescope scans large portions of sky roughly every few nights, rather than staring fixedly at one target, it functions almost like a security camera pointed at the entire universe at once. Supernovae exploding in distant galaxies, gamma-ray bursts, sudden stellar flares, and other short-lived events that earlier telescopes would often catch only after. The fact, already fading, can instead be caught right as they happen, giving scientists a head start studying them while still active. Before this kind of rapid repeating survey existed, catching one of these brief cosmic events required a fair amount of luck. A supernova might ignite and begin fading before any telescope happened to be pointed at that patch of sky, so astronomers would only catch the tail end, missing the crucial early stages entirely. By scanning enormous portions of sky every few nights and comparing each new image against everything captured before it, this observatory can flag the instant something changes, brightens, dims, or appears where nothing was previously visible, turning astronomy from occasional spot checking into something closer to continuous monitoring, catching stellar deaths and other short-lived phenomena in their earliest moments rather than stumbling across the aftermath. The third goal involves mapping the structure of our own Milky Way galaxy in far greater detail than ever before, largely using a category of star called RR Lyrae variables. These ancient stars pulse in brightness on a predictable, well-understood cycle, making them useful as what astronomers call standard candles, essentially cosmic mile markers that let scientists calculate precise distances across the galaxy. During its first test observations, the observatory had already identified several dozen of these pulsing stars, and researchers expect that number to grow into the hundreds of thousands across the full survey. Many sit out in the faint, sparsely populated outer regions of our galaxy, areas historically difficult to study because the stars there are so dim and spread so far apart. By tracking huge numbers of them, scientists hope to trace faint stellar streams left behind by smaller galaxies that collided with the Milky Way long ago, essentially reading the scars of our galaxy's violent early history. Standard candles matter because measuring distances in space is one of the hardest problems in the field. You cannot stretch a tape measure between 2 points floating in the void. Instead, astronomers rely on objects whose true brightness is already well understood, then compare that to how dim the object appears from Earth. The dimmer it looks, the farther away it must be. RR Lyrae stars are useful because their pulsing cycle is consistent enough for astronomers to identify them with confidence and calculate a reliable distance. Multiply that across hundreds of thousands of these stars scattered through the galaxy's outer halo, and you get something close to a full three-dimensional skeleton of the Milky Way's true shape, including structures essentially invisible to earlier telescopes because nobody had enough markers to connect the dots. The fourth goal is to create the most complete catalog of solar system objects ever assembled, bringing us back to those asteroids, along with comets and something even rarer. Every so often, an object passes through our solar system that did not originate here, formed around a different star, flung into interstellar space, and drifting close enough for us to notice before it continues on, never to return. Scientists have confirmed only a small handful of these interstellar visitors, each discovered somewhat by luck, spotted only days or weeks before it became too faint to study. Because this observatory scans such enormous portions of sky on such a rapid schedule, it should dramatically improve our odds of catching these rare visitors early. Potentially, while they are still far enough away to give scientists months of notice instead of just days. Researchers hope that over its 10-year mission, the observatory could detect several more of these ancient travelers, each carrying frozen chemical fingerprints from a completely different star system. The reason earlier interstellar discoveries were caught so late comes down to exactly the limitation this observatory was built to solve. Older survey telescopes covered smaller patches of sky per exposure and revisited any given patch far less often, so a fast-moving faint object on an unusual trajectory could slip through the gaps for weeks before anyone noticed a pattern. A telescope covering huge swaths of sky every few nights shrinks those gaps dramatically, so something moving unusually fast on a path not gravitationally bound to our sun is far more likely to get flagged early, while there is still time to point other major telescopes at it and study its composition properly. Stepping back to the first of those four goals, the most ambitious one involves mapping dark matter and dark energy, two of the biggest unsolved mysteries in physics, by tracking how billions of galaxies are distributed and how they move across vast stretches of cosmic time. Scientists cannot see dark matter or dark energy directly, but by measuring how galaxies cluster together and how that pattern subtly bends and distorts light from objects behind them, researchers can piece together indirect evidence about what these mysterious forces are. Both reveal themselves only through extremely subtle statistical patterns spread across enormous numbers of galaxies, not through any single dramatic observation. A telescope that studies one galaxy at a time, no matter how sharply, cannot detect these patterns, because the signal only becomes visible once you have measured the shapes, positions, and distances of billions of galaxies spread across huge stretches of the sky. Why, that is precisely the task this observatory was built for. Its enormous field of view, combined with repeated scanning over a full decade, means it will build a catalog of galaxy positions and shapes on a scale never possible before, giving physicists their best opportunity, yet to measure how these invisible forces have shaped the universe over billions of years. Now, all of this scientific ambition creates a staggering data problem, and solving it might be just as impressive as building the telescope itself. On a normal night, the observatory generates around 20 terabytes of raw data, enough to overwhelm most traditional systems immediately. Engineers built a dedicated high-speed fiber connection to beam that data from the mountaintop in Chile directly to processing centers in the United States, where automated systems calibrate images, correct for atmospheric distortion, identify anything that moved between exposures, and flag anything that changed brightness unexpectedly, all before a human scientist has even looked at the results. Over the full 10-year survey, the observatory is expected to accumulate around 500 petabytes of data, so much that fully analyzing it will likely take research teams years, if not decades, after the observing mission has ended. What makes this even more remarkable is that a significant portion of this data will be made accessible to the public, not just professional astronomers with specialized supercomputing facilities. Tools have been built to let ordinary people explore these massive images directly, zooming from a wide view containing millions of galaxies down to individual stars, the same way you might zoom around an online map. This opens the door for citizen scientists to spot something new themselves, whether an overlooked supernova, an unusual asteroid, or a faint object automated systems missed. Given how much data this telescope produces every night, more curious eyes looking through it is a genuine advantage, not just an educational gesture. This public access also represents a significant shift in how large scientific projects operate. For a long time, working with cutting-edge astronomical data required institutional access, specialized training, and computing resources most individuals did not have. By designing public tools around a dataset this enormous from the start, the project lowers that barrier substantially, letting students, hobbyists, and curious people engage directly with frontier-level data rather than waiting years for a simplified summary to trickle down through textbooks. Since professional teams will spend years working through the full dataset, even with automated help, broader participation increases the odds. Something unusual gets noticed sooner rather than later. Stepping back, it is worth appreciating just how unusual it is for a ground-based observatory to generate this much scientific excitement in an era dominated by space telescopes. For decades, the assumption has generally been that the clearest view of the universe requires sending a telescope above the atmosphere entirely, the way Hubble and James Webb both did, to escape the blurring, light-polluting effects of Earth's own air. This new observatory proves that a sufficiently well-designed, well-positioned, ground-based telescope can still compete directly with that approach, at least for wide fielding. With rapid repeated scanning. It does not replace space telescopes, and it was never meant to. Those remain unmatched for zooming deep into individual targets with extraordinary precision. But for surveying enormous stretches of sky quickly and repeatedly, watching for change rather than studying one fixed target, this ground-based approach is extraordinarily well suited to the job and remarkably cost-effective compared to launching an equivalent instrument into orbit. So here is what this all adds up to. In a single 10-hour test run back in 2025, before its real mission had even started, this observatory produced a mosaic containing millions of galaxies, revealed the hidden neighborhoods surrounding two famous nebulae, and discovered more new asteroids than most observatories manage in weeks of dedicated searching. Since then, it has kept adding to that total, uncovering objects like the fastest known spinning asteroid of its size and logging thousands more newly discovered space rocks with every survey period. And this is still just the opening act. Over the coming decade, this instrument is expected to map the structure of our own galaxy in unprecedented detail, hunt for signs of dark matter and dark energy across billions of galaxies, catch cosmic explosions in the exact moment they happen rather than after the fact, and give humanity its best chance yet at catching rare visitors from other star systems. Astronomy has spent most of its history working with narrow snapshots, one telescope, one observation at a time, piecing together the universe photograph by photograph. This observatory represents something closer to a live, continuously updating map of the visible sky, rebuilt every few nights, catching change the instant it happens, rather than after the fact. That shift from occasional snapshots to a genuine time-lapse of the cosmos is quietly one of the more significant developments in the field, even if it does not always come wrapped in a single dramatic headline. If you want to keep following along as more discoveries come out of this telescope, make sure you are subscribed and have notifications turned on. Drop a comment letting us know which part of this surprised you the most, and share this with anyone who would appreciate just how much one telescope can actually see. We will keep tracking every major discovery this observatory makes as its mission unfolds, so stick around because we are just getting started.